What if I told you that we could take one of the most high-performance but also most fragile tools in your entire kitchen and with a little bit of industrial magic make it almost indestructible? Well, today we're going to see exactly how science can take a knife's biggest weakness and turn it into its greatest strength.
It's such a frustrating paradox, right? You go out and buy this amazing tool because it's the best at what it does, only to find out that the very thing that makes it great also makes it incredibly fragile. And today, we're going to look at how to solve that exact problem.
So, the hero of our story, or maybe the flawed hero, is the ceramic knife. I'm sure you've seen them. They're usually that brilliant white color, they're super lightweight, and they are famous for being unbelievably sharp. But yeah, that sharpness, it definitely comes at a price. Okay, so the secret to that amazing sharpness is the material itself, zirconia. It's an advanced ceramic, and it's way, way harder than kitchen steel. That's why it can hold a razor-sharp edge for what feels like forever. But that extreme hardness, that's also its fatal flaw. Just like most ceramics, it's brittle. So if you drop it or twist it the wrong way, or even hit a small bun while you're cutting, that blade can literally shatter. And if you look really, really closely at a ceramic knife that's been used for a while, you'll almost always see these tiny little microchips all along the cutting edge. And these aren't from some big accident. Nope, this is just from simple, everyday use, the friction against your cutting board. With every single slice, the blade is kind of slowly destroying itself. And the damage isn't just physical. The surface of the blade is also vulnerable to, believe it or not, chemical attack. So when you cut something acidic, like a tomato or a lemon, the blade itself can actually stain and degrade over time. The very food you're preparing is slowly weakening the tool you're using to prepare it. So how in the world do you protect a super hard, super brittle blade like this? Well, you give it a suit of armor. In this case, an incredibly tough, ultra-thin coating of a really special material. And here it is. Meet our solution, chromium oxide. Now, this isn't just any old coating. It's actually another ceramic, but it's one that's prized in heavy industry. We're talking aerospace, manufacturing, for its absolutely phenomenal resistance to wear and tear. And this chart, this shows you just how insanely tough we're talking. So a standard steel knife has what's called a Vickers hardness of about 700. Our zirconia blade is already way up there at 1250. But the chromium oxide coating, it is in a completely different league, topping out at a staggering 3000. That's so hard, it is literally tougher than the super hard ceramic it's designed to protect. So the result is basically a perfect defense. This one single coating solves every single one of the knife's original problems. It resists all those little microchips, it's completely impervious to acid and salt so it can't stain, and hey, as a bonus, it gives the blade this incredible, dark, mirror-like finish. Okay, so how do you even apply this armor? I mean, you can't just paint it on, right? Fusing an advanced ceramic coating onto another ceramic, well, it requires a process that sounds like it's straight out of science fiction. It's called thermoplasma spraying, and what you're basically doing is creating a jet of superheated plasma gas. You inject powdered chromium oxide into it, which instantly melts, and then it's blasted onto the blade's surface at an incredibly high velocity, forming this dense, perfectly bonded layer. Yeah, it is every bit as intense as it sounds. But before that lightning strikes, the prep work is absolutely everything. First, the blade gets a very gentle grit blasting, and that creates a microscopically rough surface for the coating to physically lock onto. Then, it's meticulously cleaned. And finally, the polymer handle gets completely masked off to protect it from the intense heat of that plasma jet. And after all of that super intense work, the result is a protective layer that's just 30 to 80 micrometers thick. Now, to put that in perspective for you, a single human hair is about 70 micrometers thick. So this immensely durable suit of armor is, quite literally, thinner than a hair. But, a high-tech process like this, it's delicate. Fusing one material to another at these kinds of extreme temperatures is just filled with potential points of failure, especially when the final product is going to be used with food. Which, of course, brings us to the most important question of all. This is an industrial coating. Is it actually safe to have on your kitchen knife, touching the food that you and your family are going to eat?
And this is a really critical distinction to make. When people hear the word chromium, they sometimes think of the hazardous form, hexavalent chromium, or CrVi. But that is not what's being used here. This process uses chromium 3 oxide, which is a much more stable and much safer compound.
But even so, Precision is absolutely key. If that prep work is wrong, the coating just won't stick. If it's applied even a little too thickly, it can develop microcracks. The intense heat itself can cause thermal shock and crack the blade. And of course, if the process isn't perfect, you risk particles flaking off, which is a major food safety concern.
But when the science and the preparation and the application all line up perfectly, the result isn't just a repaired knife. It's a completely reimagined object.
And here it is, the payoff. You go from a chipped, stained, vulnerable white blade to this sleek, dark, high-performance tool. The edge is now completely protected, the surface is totally stain-proof, and the knife is stronger and more reliable than it ever was, even when it was new.
And you know, there's a bigger picture here too. This process isn't just about creating a cool, superpowered knife. By making these brittle blades so incredibly durable, we extend their useful life dramatically. And that means fewer broken knives ending up in landfills. It's just a fantastic example of how advanced science can actually lead to less waste.
It really makes you think, doesn't it? If this kind of transformation is possible for a simple kitchen knife, what else in our daily lives is just waiting for the right layer of science to turn it from something flawed into something fantastic? What everyday object around you is just one supercoating away from being perfect?